Okay, so we're going to study the electrostatics of point charges. We'll start with electric force. The electric force law, the force between electric charges, is also known as Coulomb's law, and it has a structure and a form similar to the law of universal gravitation, which says the force between any two masses in the universe is given by an inverse square law and varies directly with the two masses. So the law of electric force is similar in that there's a universal constant, which is K, the electromagnetism constant, 9 times 10 to the 9 Newton meters squared per Coulomb squared. Then there's the product of the two charges, Q and Q, and it's an inverse square law. Now, because charges can be negative, we'll put an absolute value here, so that this just gives us the magnitude of the force. The direction of the force just comes from, let me just put force equals here. Oops. Clear. Force equals. There we are. The direction of the force just comes from the law of electric charges, which says quite simply that like charges repel and unlike charges attract. And based on that, we can do force diagrams here very simply. These two charges will repel each other and these two will attract, so the force diagrams will just look like as follows. So in the first case with the two positive charges, the electric forces are one to the left, one to the right. And then here, with attraction, the force on the positive is down and the force on the negative is up. For this example right here, where we're asked for the force diagram for the positive charge, there'll be two attractive forces, one towards that negative, i.e. to the right, and then one downwards. If all the charges have equal magnitude, then this force and this force will be the same, and you'll end up with a resultant that's in this direction, which is just the vector sum of those two. And it's a 1, 1, root 2 triangle, so it will be root 2 or 1.41 times greater than those two forces. Okay, so an example, a helium ion. So we want to first figure out what the radius is, and we can do that using the Bohr model. We know that the radius of the nth orbit energy level is 53 picometers times n squared over z. So R1, the ground state for helium, the atomic number is 2, and the ground state will be 1, so this gives 53 over 2. This gives 26.5 picometers for that orbital radius. And now we'll apply Coulomb's law. Coulomb's law just says that the force on the electron is kqq over r squared with the absolute value. Big Q might be the nucleus. Now in helium there'll be 2 protons and 2 neutrons. The 2 neutrons don't contribute, the 2 protons do. So there's positive 2 fundamental charges in the nucleus. The other charge will be the electron, and that has a charge of negative 1 fundamental charge, where E is, of course, 1.60 times 10 to the negative 19 coulombs. So putting in the radius that we just computed, we can substitute and find the amount of force on the electron. So it's 9 times 10 to the 9 Newton meters squared per Coulomb squared. That's the K constant. And then absolute value, so we can drop the negative sign. So we're going to have 3.2 times 10 to the minus 19 coulombs. That's the nucleus. And dropping the minus sign on the electron charge, 1.6 times 10 to the minus 19 coulombs. And then we divide by the radius, which is 26.5 picometers. So that's 26.5 times 10 to the minus 12 meters, all squared. Unit-wise, Coulomb and Coulomb cancels out Coulomb squared. Meter squared cancel. You're just left with a force in newtons. And I get 6.56 times 10 to the negative 7 newtons. Okay, another force problem. Let's find the force on the electron shown below. So here's an electron. That's a negative charge. And there's going to be two forces, one from this negative charge and one from this positive charge. So let's start with the force diagram. So this negative electron is going to be repelled from the first charge, and it's going to be attracted to the second. And because the two charges are the same and the two distances are the same, both of these forces will have the same magnitude. So what is the magnitude of those two? Well, it's going to be k qq over distance squared. Now, the first q, they're 1 microcoulomb, so that's 1 times 10 to the minus 6 coulombs. The second q, that's the electron, as a negative e charge, so it's minus 1.6 times 10 to the minus 19 coulombs. Now, we have to substitute. Oh, and the radius or distance, it says 2 micrometers. That's 2 times 10 to the minus 6 meters. So we'll substitute 9 times 10 to the 9, absolute value, because we just want the magnitude. The minus sign doesn't give us any information about magnitude, so we drop it. 1 times 10 to the minus 6, 1.6 times 10 to the minus 19, 2 times 10 to the minus 6 meters squared, and we dropped units because we had units in the previous question, and they are the same here. So that works out to 3.6 times 10 to the minus 4 newtons of force. So there's going to be 0.36 millinewtons that way, 0.36 millinewtons this way. So if we find the resultant, 3.6, we see it's really a 1, 1 root 2 triangle. So this will just be root 2 times 3.6. And that works out to 5.09. This angle here works out to pi over 4, or 45 degrees. So the resultant force then on the electron is root 2 times 3.6, which is 5.09 times 10 to the minus 4 newtons at pi over 4, or 45 degrees that way.